Welcome back to Physics 141 Online. Before diving into specific example problems of collisions where we apply the conservation laws of momentum and sometimes of kinetic energy, I'd like to finish presenting the new material from this chapter and first just speak briefly about how to calculate the center of mass of a continuous object rather than a system of point particles. So how do we find the center of mass of an object like that where the mass is spread out in space? So if a continuous object has a uniform mass distribution, what we can do often is break it down into smaller pieces if the individual pieces have simple shapes, and we can find the individual center of mass positions of those pieces, and by then weighting the positions of the center of mass of the pieces by the mass of the piece, we can find the center of mass of the whole object. For example, look at this L-shaped piece of plywood. Imagine that we have this piece and maybe we've gotten it from the scrap heap and we want to find where the center of mass is. So what would we do with that? Because it doesn't appear very easy for us to apply the simple formula that we learned for point particles. However, what we can notice is this L-shaped piece is made up of two rectangular pieces, one oriented vertically, the other one oriented horizontally. And if these pieces are uniform, if they're evenly distributed for the mass all throughout, then we could identify the center of each piece. And let's say that the vertically oriented piece has a mass m1, and we could treat it as if all of its mass were at the center. And we could do the same thing for the second piece, whose mass might be m2. Its center would be here. And so what we then could do is treat this as if we had two single point particles, one of them with mass m1 located at the center of the top object, the other one with mass m2 located at the center of the bottom object. And at that point, all we would need to do is apply our simple center of mass formulas. However, there are cases where the object is non-uniform, which means maybe it's heavier on one side than on the other side, or its shape is complicated enough where we can't break it down into just rectangles and triangles and simple shapes. In that case, although we're not going to show examples of this, I'll just show you the plan of attack. We would actually use calculus in order to add up the contributions of each of the pieces of the object to find the center of mass position. So imagine that you have an arbitrarily shaped object, maybe something even wilder than this, where we wouldn't necessarily know where the center of mass is just by inspection. What we do, and this is what calculus is good for, is we break the object down into tiny little pieces. I'm greatly exaggerating the size of this piece in my red square, but imagine then saying that this object is composed of lots of tiny little squares, each of which has a mass delta m, and they all add up to give you the total mass m. So what would we do? To find the center of mass position, normally if this object were composed of discrete point particles, we would sum up the mass of each particle times its position and divide by the total mass, and that would give us the center of mass position. Here, what we're going to do is break it up into these little pieces, each of which has a mass delta m, so that the sum would be delta m sub I times r sub I, the position of that piece. But we're now going to use calculus notation to take the limit of this sum where the delta m gets smaller and smaller and smaller and eventually goes to 0. And so what we have in that case is basically an integral. The limit of a sum where the pieces that are involved in the sum get smaller and smaller is an integral. So the center of mass position would be calculated, and I'm not going to show you how to do this, but just mention how it would be set up. It would be done by integrating the position vector associated with each piece multiplied by this tiny, tiny little mass of each piece. dm is the infinitesimal mass associated with each of these very, very small pieces. And there are techniques for doing those kinds of calculations where we then would divide by the total mass of the object, and so we would find ultimately the center of mass position. So I wanted you to see that. You might run into that a little bit later on in your studies of science or engineering, but that's how we would approach that kind of a problem. Now, the last new topic that I'd like to introduce today is impulse. And impulse is just a quantity that's defined because sometimes we would like to be able to answer a question in a quantitative way. A question like, how hard did the batter hit the ball when he swung and sent it flying into the outfield? And so to answer questions like that, another similar question might be, how much impact did the collision of the car with the wall have? What did that do to the car? And so the impulse is defined, and the symbol used for that is J, and it's a vector because it's defined as the final momentum of the system minus the initial momentum of the system. So it's just delta P. Remember, as we're going through this part of the course, that momentum is a vector. It's got not only magnitude but direction. And as a result, impulse has a direction associated with it as well. So in order to flesh this out in a little more detail, to relate the change in the momentum to some other quantities, we can rewrite Newton's second law in a very useful form. So remember, Newton's second law said the net force, the sum of all the forces acting on an object, is its mass times its acceleration. And if we substitute for acceleration as the derivative of velocity with respect to position, and then realize that, that mass that's multiplying the velocity derivative can actually be brought inside the parentheses here, so that we're taking the derivative with respect to time of the product of mass and velocity, then mass times velocity, we've already defined that as momentum. And so we see that a more general version of Newton's second law can be written this way, as the net force acting on an object is equal to the time rate of change of momentum. So what this allows us to do is now write an expression for the small change in momentum associated with a net force acting on an object over a small amount of time. So I'm solving this equation for dp to get an expression for this tiny change in momentum when a net force acts on an object over an infinitesimal amount of time. And of course the reason I do this is because I would like to now sum up the influence of this force over a finite amount of time in order to get the total change in momentum. So integrating this quantity from an initial time to a final time gives me p final minus p initial, which is just delta p, as the integral of the net force dt from t initial to t final. So this result is often written in terms of J, and people call it the impulse momentum theorem. So we define J to be the change in momentum, and now we see how that is related to the influence of a net force acting on an object over a certain amount of time. And I'd like you to compare this to something that we've seen already, because you'll see similarities in it, and that is the work-energy theorem. Remember that the work-energy theorem, once we defined what we meant by kinetic energy, the work-energy theorem said that the net work acting on an object is equal to its change in kinetic energy, and that's equal to the integral of the net force dotted into the displacement as the object is moving from an initial to a final position. And so you'll notice that both the impulse momentum theorem and the work-energy theorem relate changes in an object's motion. In the top equation, it's the change in momentum. In the bottom equation, it's the change in kinetic energy, which means the change in speed. And they're related to the influence of the net force. In the top equation, that net force, we have information about how it acts on an object over a certain time, while in the bottom equation we have information on a net force acting on an object as it moves between two positions. So which one we use for a given problem just depends on the available information. So one more thing with the impulse momentum theorem, sometimes that net force changes with time in a really complicated way, and we can't necessarily predict what that's going to be in advance. And so sometimes we'd like to relate the change in the momentum not to the specific details of a changing force, but maybe just the average force that acts between these two times. And so we can take that relationship for delta p as the integral of f net dt and just say we'll set that equal to an average force acting on the object between t initial and t final. And so that comes out to be just the average force vector times delta t. And this expression is helpful when we're looking at collisions maybe between a bat and a ball, where we know the initial momentum of the ball as it comes toward the bat, and we know the final momentum of the ball as it leaves the bat. And if we know the time during which the bat and the ball were in contact, we can use that information to calculate the average force that the bat exerted on the ball. And you can see your homework assignment for an example problem just like that. I hope this has been helpful, and I will see you in class.